Okay, here we go. Office hours. We're doing some questions from the quiz. There's another chair. You can also take my chair if you'd like. Question 3 from quiz 1.
It's taking like a second to load. Sorry.
Yeah, no worries.
You want me to see it? Oh. You want me to see it?
I think let's see if I have it. Oh, it's because I'm on.
Oh, yeah, the Wi-Fi in this room is not great. I actually use an Ethernet cable because it doesn't work great.
Yeah. Okay, so the question is, what mass of Na2CO3, and then it gives the molecular weight of 105.9 equals, the molecular weight equals 105.9 grams per mole, and then should be used to make 2.5 milliliters of 0.057. I think it's just molar of Na2CO3.
2.5 milliliters of
0.057 molar of Na2CO3.
Okay. Slow wave, fast wave. How fast do you want me to go through this?
Slow way.
Okay. So slow way, we're going to go ahead and do the thing I like to do whenever I don't know what I'm doing in a problem, and I break it down. Well, I can even write it down the right way. Getting ahead of my head itself. We get our explicit information. We get the result we're going for. And we look at what's the mysterious thing in the middle that the problem's trying to get us to think of. And the reason I like doing this logical processing for problems is because it works outside of chemistry classes too, right? You can do this for pretty much any problem, not just in school, but in your life as well. You can be like, okay, what's the information I have? What's the result I want to get to? What's the stuff I don't know that I need to figure out in order to make that happen? So here I'm just going to write some things down. I've got the molecular weight is, I'm just going to call it 106 since I'm feeling like that. I have a volume equal to 2.5 milliliters. I've got a molarity equal to 0.057, and I want to know some grams of, I can call it sodium carbonate now, and everyone's okay with that? I want to know the grams of sodium carbonate. The implied things in this case are how we use these different things. So knowing that molarity times volume equals moles is going to be the first thing that we have, right? That's the molarity is moles per liter, so that's just rearrangement of the molarity equation. And then also, molecular weight times moles equals grams, right? I got moles on bottom of molecular weight. If I multiply by the number of moles, that gets me my grams. And so with that, just by getting those two pieces of implied information, keeping in mind these are rearrangements. Molarity equals moles over volume, I rearranged that. Molecular weight equals grams over moles, I rearranged that. But with those two rearrangements, we're actually in a really good position to solve the problem. And I kind of had a hunch I was going to use those two things, because I was given volume and molarity. That suggests that equation to me. And then I had molecular weight in grams, and those two things suggest that equation to me. So I can go ahead, there's two different ways I can approach this. I can do step by step, or I can cram everything together at once and then do the numbers. I'm going to do step by step because it feels safer. At this point, I just do a couple other things that are implied, right? And I've gotten pretty lazy with writing these things down as implied information because it's just things I hope we know at this point. But other things that are implied, since this was from quiz 1, this was one of the implied ideas. 1 liter equals 1,000 milliliters, right? Those conversions are things that I just assume you know at this point, right? I figure, oh yeah, you know how to convert. In this quiz, that was actually one of the things that I was mostly looking for was, can you recognize when you need to convert and what to convert? So I've got to convert my volume because my molarity is in units of moles per liter, my volume's in milliliters, I have to do that conversion. So I take my milliliters, I convert to liters, 0.025. Just here, should I do that? Multiply by the molarity, the molarity, 0.057. That will get me some number of moles if I had a calculator handy.
Could you explain why you knew that you'd have to do that conversion one more time?
So when I look at the units that I have been given things in, capital M molarity is units of moles per liter, and this can be considered another implied thing, right? That means moles per liter. So right away, I can notice that I've got two different volumes. I need my volume units to match up, so I either need them both in milliliters or both in liters. And I don't like switching things on bottoms of fractions, so I switched the milliliters to liters, and then canceled out the volume. So I have 0.0025 times 0.057. Is this looking familiar to what you did in your process?
No, no, I forgot to. I think what I did is I forgot to convert milliliters to liters. So I got like a weird answer at the end.
Okay, well, let's see what your weird answer was and how it compares. Because if that's all you forgot to do, you're going to be off by like a factor of 1,000.
It might be something else. I just want to see which
Yeah.
you.
So I get this for my number of moles. Right, so I know how many moles of sodium carbonate I have in my solution that I'm going to be making. And I have to figure out how many grams of sodium carbonate do I need to get that number of moles. Given that it's a kind of small number, I'm expecting something on the milligram scale because it's on the 10 to the minus 4. But let's go ahead and figure that out. 1.425 times 10 to the minus 4 moles of Na2CO3 times my 106 grams per mole. You can see my units of moles cancels out, and I'm going to get something in grams. And that becomes 1.511 times 10 to the minus 2 grams. So 15 milligrams. I don't know, did it ask for the answer in grams or milligrams? Did it specify units?
Mine says milligrams.
So in that case, we've got to do one more step to finish this. Right, and we always have to be careful for the units it asks for. The units are usually a hint, right? So if it's asking for an answer in milligrams, I should get an answer that's probably between 1 and 100 milligrams. Otherwise, it asks for the answer in grams, right? So that is actually, even though it doesn't seem like a useful piece of information, a big part of chemistry is realizing how each thing is useful information. Like in the nomenclature we're starting to learn about, like the nomenclature when we first learn it seems like this kind of like heavy, like why do I have to learn all these different ways? But the names are actually hints to the structures. They're telling you something about the type of bonding, the type of interactions that are there. So last thing, and I've gotten pretty good at doing these in my head, so here's my quick way of doing this. I'm just going to turn this to 15.11 times 10 to the minus 3 grams. And then I know that 10 to the minus 3 disappears to make it 15.11 milligrams. That's how I do the conversions really quick in my head. Is I change my number from whatever scientific notation I have to the one of the ones I know, and then I can just drop it for the prefix. And I could add an extra step in here. Let me add the extra step and show you why that works, right? So the extra step that I start to skip is I'm going to multiply by 1 milligram is 1 times 10 to the minus 3 grams, right? So then the 10 to the minus 3 just cancels out, and I just get 15.11 milligrams. But I do that canceling out of the prefix in my head.
Question.
Yeah.
How much are we able to rely on our equation sheet for formulas, such as the implied formulas given here? Like, would we be able to mainly rely on this, or?
Yeah, I mean, yeah, you should be really comfortable with your equation sheet. A lot of these equations are on there. Some of these earlier things from week 1 where we were learning unit analysis are not on there. Like all of the unit conversions, I don't know if the definition of molarity is on there. Let me look at the equation sheet real quick and see what's even on there. Right, so you've got the dilution equation, but you don't have the molarity equation. You don't have the equation for molecular weight. You don't have the equation for density. Those kind of simpler equations, those are things that I expect you to know already.
Gotcha. Maybe if we have time, and it's chill if we don't, but could we gather a list of the equations that we'll need, and just like maybe write them on the back?
Yeah, if we have time, we can go through that. I don't know if there's many more than are on there besides the ones I just talked about.
Sure.
What answer did you get?
I got 100. I got 151. So I'm gonna just
151.
I got 20, but I can't find the paper that I had my work on, and it's right.
Yeah, I can't find my worksheet.
They're
either.
different because I have 66.9.
Oh yeah. Oh, all the
But they're
numbers are
all
randomized.
different.
All the
Oh,
numbers are
okay.
randomized.
Oh.
Yeah.
On the quizzes and things, all the numbers are randomized,
Yeah.
and the graded questions, all the numbers are
Yeah.
randomized.
Okay.
So you should have different answers.
Okay.
Yeah.
I wish I
You're
had.
151. Can I see your work real quick?
I don't have my scratch work, but
Oh.
I just have like the answers from the lab.
Yeah. So
I wonder if it was just
Oh yeah, my moles.
because I did those conversions.
yeah, I would have to see your work to
I
figure
wonder
out
if it
where
was
it
like a
went.
calculator thing.
You know what? The terrible part is it could really be as simple as you had like 1.511 times 10 to the minus 2, but you turned that into 151 because you saw the minus 2, you did a plus 2. It could be something like where you did all your work right, but then when you entered it into LabPal,
It just I just like
yeah,
yeah.
you just
okay.
moved the decimal the wrong way. But it's really hard to tell without the work, but it sounds like you're on the right track and you just have to be careful with your conversions.
Mhm.
What's your major?
I'm Earth and Soil.
Okay, well, not like for the people who are like pre-med and stuff like that, I'm like, if you give someone 15 grams versus 15 milligrams versus 115 milligrams, you could poison them.
Yeah.
Earth and soil, depending on which route you go, you can mess things up pretty bad if you're off by an order of magnitude.
Okay.
I shadowed a vet clinic,
Yeah.
and the doctor has me like take out meds and all of that, right? And he'll be like, okay, so this dog weighs this many kilograms, but the dose is like this milligrams per liter or something like that. And I'm like, he's like, yeah, stoichiometry is really important.
Yeah. Earth and soil, when you're doing sample preps and stuff like that, if you're doing like soil analysis, if you over dilute or under dilute your sample and you end up with the wrong concentration, then you're like, oh, this soil doesn't have any calcium in it. Should we look at number 5?
Yes.
Any questions on this one before we say?
I just wanted to make sure I was doing the right thing.
Process looks good. Looks like you got to be more careful with your zeros or your entries. Okay, looking at number 5.
Okay, we're given like an unknown solution that has a maximum absorption peak at lambda max 630.4 nanometers with an absorption of 0.824 AU in standard spectrometer. Yeah. If the solution was made by placing 23.99 micromoles of dye in a 250 milliliter in 250 milliliters of water, what is the molar absorptivity for the unknown dye?
Okay, so okay, so couple big things that we can see, right? I'm just going to jump straight to the implied here. We have an A, we have an epsilon, that's going to be Beer's law. We have it as a standard spectrometer, so path length is going to be 1. We have the absorbance given to us. We're trying to find epsilon. So there must be some way that we can figure out what the concentration is, right? Concentration is going to be in units of molarity, so that's going to be moles per liter. So that's going to be equal to my 23.99 divided by 250. Not forgetting my conversions, right? I can just erase the million, have that times 10 to the minus 3. I can take the micro and have that times 10 to the minus 6. And that's going to be 23.99 divided by 250 with an extra 10 to the minus 3 there. So we do that. 23.99 times 10 to the minus 6 divided by 250 times 10 to the minus 3. And I get my concentration is equal to 9.596 times 10 to the minus 5 moles per liter because that's not now, liter, because I did both of my conversions. Then I go ahead and I plug my concentration in, rearrange, so I've got A over BC is equal to epsilon. Inverse this times 0.824. Epsilon is equal to 8.5 0.87 times 10 to the positive 3. This would have units of inverse molarity per centimeter. I don't think it asks for the units, but I think units are important. So like 8,000 is a little bit below our typical range of 10,000 to 100,000, but still reasonable.
Okay.
What answer did you get?
I got 2,077, but I was kind of lost in how to find E.
Did I go too fast, or was that okay?
Can you explain again how you got the C equals mole over liters? Like, is that just a standard?
That's just concentration, right?
Concentration.
So, and the reason we use C in this equation instead of M in this equation is because there's actually multiple ways that you can write down concentration. Molarity is the one that we're using, moles per liter. You can also have parts per million. You can have molality. You can have percent by weight. This is a really handy one if you're making big mixes. But we're using molarity. Molarity is the one that's kind of most convenient for doing calculations on paper, but it's not the most practical in laboratories. So in laboratories, you'll see things like molality or percent weight. Percent weight is really nice in laboratories because you just weigh out the masses of the two things and mix it. Like you measure the mass of this liquid, the mass of this liquid, dump it together, and that's the percent by weight. And so that's a really easy one to do laboratory-wise, but it's not an easy one to do in terms of calculating number of moles. So that's just concentration is moles per liter is specifically looking at this for molarity.
And then another question with beer is, are you allowed to switch the variables around? If you, like, let's say you want to try. Oh wait, we already know concentration. Will always be just one?
Unless we do something really weird, right? As long as we're using a standard spectrometer, it'll always be one. I actually looked up an example. I was trying to come up with problems. This is not one of the problems I put on the exam, not this one in particular, but I was trying to look up problems. And I try to make it related to the real world. And I found someone who is using a spectrometer, like this, like a UV vis spectroscopy, to measure the amount of ammonia in the atmosphere above animal, like, I just forget the name of it, but like the animal slurry pits from like the livestock areas. Because like there's a lot of like, as all of that like mess kind of decomposes, a lot of ammonia comes out. And so the way they did it was they had to set up a couple mirrors and bounce the light back and forth, so the light ends up traveling something like 3 miles above so they can have enough sensitivity. And so in that case, your path length ends up being 3 miles.
That's like a specific example?
Yeah, and that's because when you're doing this for gases have such low concentration, and you don't want to like, well, it was funny because I was reading the paper and I was like, kind of seems like it would make more sense if you did like air collection, so you could concentrate all of that and then dissolve it into a liquid and then do liquid spectroscopy. But they were doing direct air measurement, so they were setting up essentially like they have this big thing that they pretty much like move into it's on this like lift, and they can lift it into the air, and then as the gas passes, they just pass the laser through it, and then they can truck it over it like it's on the back of a truck, and then they can drive it over to the next place and test the ammonia over at the next place.
Where was this?
I don't remember. It was like a paper that I was looking at this weekend.
Oh, okay.
I was just kind of like curious, like looking through things, trying to find real world examples of like spectroscopy and of like the periodic trends and like all the things we've done, emission spectroscopy, absorptions. I just try to find something new to like look at, like, oh, what's something that you could do with this that might be interesting to people. My past examples, like when I'm teaching a 124, I taught a 124 class last quarter, very similar content. But when I'm doing that one, I'm always like, oh, what kind of like microprocessors, what kind of like solid materials, like I just go a different direction. So.
And then like ones like times 10 to the negative 6, those conversions we'll have to like memorize.
Yeah, and there's 5 that I encouraged you to remember. Kilo being 10 to the positive 3, centi being 10 to the minus 2, milli being 10 to the minus 3, micro 10 to the minus 6, nano 10 to the minus 9. Right? And there are lots more besides that, right? You can go from kilo to mega to giga to tera. Most of us are familiar with that because we care about how many gigabytes our phone has and all that. Nano, you can go smaller than nano to the pico and femto and atto, like you get really small. None of that. Like this is the range that we're usually using. The nanoscale and the nanoscale is really important on the atomic scale when we're looking at light, but the kilo centimilli, that's like benchtop measurement scale. Other questions before we pop over to quiz 2?
I have one on quiz 1 if possible.
Sure.
Number 2, I don't think I need that lengthy of an explanation, but I just like a slow walkthrough.
Okay, if I erase this while we do number 2?
Yes.
Okay. Okay.
Seems like a volume problem. Measuring, a graduated cylinder.
Number 2. Oh, is it the graduated cylinder one?
Yep.
Go ahead, give it a quick read.
A 10 milliliter graduated cylinder has an inner diameter of 14 millimeters. What is the vertical distance between the 0.10 milliliter marks on the side of the beaker? Give your answer in cm.
Okay, so the crux for this problem is kind of 2 parts. Part number 1 is the fact that we know that the volume we want to measure is 0.1 milliliters, which we can say is 0.1 centimeters cubed. Right, that's the first part. Is like it tells us the volume it wants us to measure. Part number 2 is recognizing that we know it's a cylinder, so that the volume is going to be pi r squared h. We have to be careful because this is in millimeters and it's the diameter. But now I just set these two things equal to each other. Pi r squared h is equal to 0.1 centimeters cubed. Make sure I get my radius correct. I'm going to convert, because this is in centimeters and it's asking for an answer in centimeters, I'm going to take this thing and turn it into 1.4 centimeters. I'm going to divide it by 2 to get 0.7 centimeters for my radius.
How does the problem change when you put centimeters cubed?
So let's see, right? So the whole idea is over here, if you look at this, r times h, if I have it centimeters times centimeters times centimeters, that gets me my centimeters cubed.
Okay.
Right, so it's just a matter of making sure I've got consistency with my units. If it asked for an answer in millimeters cubed, it would probably be easier to turn this into millimeters cubed, convert that volume. If it asked for an answer in like meters cubed, right? Meters cubed would be a silly way for it to ask for the answer. But if it asked for the answer in meters cubed, I would want to convert this one and this one so that all of my units are in meters.
Sure.
Honestly, if it asked for the answer in meters, I'd probably do everything in centimeters and convert at the very end, because I think that would be easier for me. And that's part of this unit analysis, is just kind of doing it enough that you can see where the path of like the easiest spot to convert is.
Sure. Gotcha.
So I'm looking for that consistency in units, since I want my height in centimeters and I've got my volume in centimeters. I'm just gonna, this is just one number to convert, so that was the easiest for me.
Sure.
So I convert that, then I plug things in. I'm actually gonna rearrange before I plug in. I'm gonna have h times 0.1 centimeters cubed divided by 3.141 times 0.7 centimeters squared. So the centimeters squared is going to cancel out 2 of the centimeters up there. I'll end up with just centimeters left over. And I'll just plug it into my calculator, see if I get a reasonable answer. 0.7 squared. Ooh. I get a height that's pretty small. 6.497 times 10 to the minus 2 centimeters. This seems like it would be better if I put the answer in millimeters, because it's a pretty small centimeter marking. But keep in mind, it's a pretty small volume, and if you remember what the graduated cylinder, the 10 mil graduated cylinders look like, the distance between the marks is pretty small. Oh, I am concerned that I did something wrong.
No, mine's really small too, because I got
Okay.
a .0789.
Yeah, so this one would be 0.0649. Yeah, I guess that makes sense.
Gotcha.
Honestly, for me to make sense of it, I need to like hold a 10 milliliter graduated cylinder and be like, oh yeah, that is small. Okay. Right, and again, finding that connection to physical reality actually helps quite a bit. Ready?
Yes.
Okay. Let's look at the the problems from quiz 2. And then we will look at effective nuclear charge in 2.2. So we're looking at quiz 2. Number 3.
All right. Green dye number 3 has a molar absorptivity of 3.43 times 10 to the 4th power molar to the power of -1 and centimeters to the power of -1. And then a molar mass of 658.5 grams per mole. What mass of green dye 3 in milligrams would you need to prepare a 1.37 liters of an aqueous solution of green dye with number 3 with an absorbance of 0.509?
Pretty similar to the quiz 1 number 3. Right? This is adding some extra steps compared to the previous quiz. The previous quiz was like you do this division, you solve. This one we kind of have to do 2 different steps to make this work. But we're gonna again have the same type of implied information, right? I'm gonna have Beer's law, A equals epsilon BC. I want to know, let's see here, I need molecular weight times moles equals grams. That's the thing I'm looking for, right? We're looking for how many grams. Looking for the grams to prepare, so I'm probably going to need that equation at some point. And then I'm also going to need, I've got a volume and an absorbance. I'll probably need molarity times volume equals moles. Actually, this works out when I start looking at this as differently as it's worded. It's the exact same problem, actually. Right? Except for instead of solving for epsilon, I'm solving for moles. It's just changed which variable we're solving for.
So we have to find the concentration.
Yeah, so okay, now if we start plugging things in, I'm going to put 0.509. I'm going to divide by B and epsilon, so the path length is 1 again. Epsilon is 3.43 times 10 to the 4. That's going to give me concentration. Then I do concentration times volume gets moles. Moles times molecular weight gives me grams. So this is recognizing that these 2 problems are, from my perspective, the same problem. This is one of the things that is difficult for students when I say, oh, we've only covered like, this quarter we've only covered like 3 topics so far. But the way I categorize problems together and the way you all categorize problems together is different. So I don't see these 2 problems as like really different. I see it's like it's the same problem, just different directions. Should I finish it out? You see it so.
No, that makes sense. So then so if we're finding just concentration, the formula is C equals A over
Epsilon.
B times E.
Yeah. B times epsilon. That gets a C. Our C gets plugged in here. We multiply by this volume. That's going to get us a number of moles. Number of moles times that gets us our grams.
Gotcha. Okay.
Now, since this is a green dye with a pretty high molar absorptivity, does it ask for the answer in grams or milligrams?
In milligrams.
I would guess that we'd need milligrams of sample to make this work.
Okay.
Just because of, like, dyes usually absorb light really well. Like 34,000 is like, that thing absorbs light really well. So we probably don't need a lot of it to make a solution that absorbs light pretty well.
And then what is molar to the -1 centimeters to the -1?
Okay, so that is a different way of writing 1 over molarity centimeter. Right, and the reason they do it that way is because then it fits into a single line of text better than doing the fraction. there's quite a few things in chemistry that I am convinced are the way they are because of old typesetting. Like, I
Makes sense,
think, like, and I don't see anything that, like, verifies that historically, but I'm just convinced that some of the ways we write things down is like, well, you can't put that into a typeset easily, so we're gonna just change the way we write it. Like the 2+ versus the +2. I've heard other people kind of give an explanation of like, oh, 2+ is communicating something about charge and +2 is like oxidation state or something like that. I think it's the typeset. Special characters don't fit in well, so you put the special characters at the very end, so you do 2+.
Gotcha.
But I can't find anything to, like, confirm my suspicion that it's typesetting is like some of the reasons we have these different notations. But the M-1, CM-1 typesetting in fractions, oof, rough. So that gets rid of the fractions, and now you're just doing that typesetting.
Gotcha.
Question.
Could you just explain what N is? I forget what that's supposed to
N
represent.
stands for number of moles.
Number of moles?
That's the variable for number of moles. V for volume, N for moles, M for mass.
Yeah,
I often drop G for mass because I'm thinking in grams, but I should be more consistent and use M for mass.
Gotcha. How would that differ from moles? I thought lowercase m was moles.
Lowercase m?
Or no, my bad, uppercase m.
Uppercase M is molarity, moles per liter.
Sure.
Right, and all of these little details become important to keep track of. So that's number 3. Yeah.
So you're just trying to find the concentration?
Yeah, so that's the next step. After that, it kind of like, for me, after I find the concentration, the rest of the problem flows. But let's go ahead and finish it off real quick. So we find the concentration point 509 divided by 3.43 times 10 to the 3rd gives me a concentration of 1.484 times 10 to the minus 5. So it's going to be like 14 micromolarity. Then I take my concentration, my 1.484 times 10 to the minus 5. I multiply by the volume, that's 1.37 liters. Because this is in moles per liter, that's going to get me a number of moles. So I multiply by 1.37, and that gets me just a slightly bigger number, 2033 moles. And multiply by the molecular weight of, oh wait, whoa! Times 10 to the minus 5 moles times the molecular weight of 658 grams per mole. That's going to cancel out the moles and just leave me with grams. Everyone's coughing.
I know, it's scary.
So
I haven't gotten sick here yet.
That's great.
I know. My roommate's sick right now, and I'm like, she's gotten sick like probably 3 times, and I've never gotten it once.
Like first quarter easy?
Yeah. I know.
I
She
had a
doesn't
really
use that
long
Chinese
healthy
system.
streak, so
What?
1.33 times 10 to the minus 2 grams, which is 13.3 milligrams. I had a really long healthy streak since the pandemic
And then
because I was masking. Like, I was one of the weirdos who kept masking when no one else was masking.
it
Like,
helps.
because, like, I'm sorry, but all y'all travel all over the country and then come back and you're all coughing and none of you are wearing masks, and like, it actually, like, I used to get really, I used to just accept it, that I was like, oh, I'm always gonna get sick at the beginning of the quarter and the end of the quarter. Like, it just happens every quarter. And then after the pandemic, like, so after the pandemic when I was masking, I was like, wait a minute. What was it, like 21, 22 was the first year we were back. I was like, I didn't get sick this year. I was like, I should just keep wearing a mask. And I didn't get sick for a really long time. I got sick for the first time in ages this winter break while I was flying back from Australia.
Mm.
And it was just like air travel. There was
Yeah.
somebody on the plane behind me coughing for the entire 13-hour flight. And it was just kind of like, that's not going to go great.
Yeah.
And so I was sick like that first week. Like, that's why I was masking at the beginning of class, not because I didn't want to get sick, because I didn't want to get you all sick, but now we're all sick anyway.
Wait, don't say that.
Sorry.
I have midterms this week and next.
Yeah. So that's why I was like, oh yeah, once we kind of do that implied information, it's like, oh, use the first equation to find concentration, plug it into the third equation to find moles, plug the moles into the second equation to find grams. Right? And so for me, it's kind of like one of the things I encourage for all of you to practice. You do need to practice making sure you can punch things into your calculator correctly, all of that. But really, just figuring out this implied stuff faster, not all the calculator work. It's just like, can I see like my path forward and be like, oh, I exactly see how I'm supposed to go. Let me go make sure I can do that with another problem. That's the part that's usually the most difficult. That's usually the part that's slowest for students. You know, the reason I talk about this, like how do we pull the problem apart, is because the part that is slowest for students, slowest for me too, if it's a problem that I didn't make, is the time from reading question to understanding what I'm supposed to do is like the slowest part. After I get that, I'm like, okay, then I can finish it pretty quick. But that slow part, so anything we can do to speed up that slow part, and this whole like explicit result implied, that gives me like an approach every time where I'm like, okay, I know how I'm going to start it every time. And so it speeds up my process. And I try to show you that so you can, if it works for you, great. If you've got your own system, do your own system. That was number 3. Should we look at number 4? Ready? Did it log you out?
I have, is it the...
It's just, this one's super fast. It's just, I got it, it's on isotopes. I got it wrong. I just want to see why I got it wrong. It talks about Fe3 plus. Iron plus 3. And so it's just asking for electrons, protons, and neutrons.
Just Fe3 plus, no other symbols on it?
56 on the side too.
56 on the side. Okay, that's important.
Yeah.
Okay, so we're looking at iron 3 plus. There it is. We're looking at iron 3 plus. First thing is, if it's iron, I know my number of protons has to be 26. I know that my number of protons plus my number of neutrons has to add up to 56, which allows me to figure out my number of neutrons is equal to 30. Right?
Yes.
Then for my number of electrons, if it was neutral, it would be 26. If it's plus 3, I need 3 less negative charges. So it should be 23. Did you add electrons instead of subtracting electrons?
No. I just swapped the order of things.
Oh no!
So I got all the right numbers. I just put for electrons 26, protons 30, and then neutrons 23.
Oh!
So I just did the wrong order, yeah.
Yeah. That's rough.
But I just wanted to make sure, like,
You understand it though,
Yeah.
so again, like just making sure we're reading carefully and not rushing too much. I know it's hard to do when you've got like a time frame and everything like that, but if it's an extra, like, you know, like I think for me, again, different people take tests different ways. For me, it's I rush through all of the problems as fast as I can, getting all of the points I can as fast as possible, and then I do a slow check through.
Yeah.
So I try to make sure I finish everything with enough time where it's like, if there's a problem where I'm like, whoa, I know I don't know how to do that, I come back to it after I do my check through. So I get all of the points that I'm confident in first, get all that taken care of, be like, oh, I know how to do that one, it'll just take me a minute, I know how to do that one, it takes me a minute. And then I'll go back and make sure I didn't make any silly mistakes like that. One of the things I will warn you all about, because is changing your answer, right? If you, like part of what we've been doing all quarter is building our chemical intuition and kind of our sense of like what a reasonable answer is. So if you get an answer and you're like, okay, that's my answer. If you go back and you're second guessing yourself and you're like, wait, what if I made a terrible mistake? Unless you see something obvious, where you're like, oh, it was diameter, I forgot to divide by 2 to make it radius. unless you see something obvious, stick with your first answer. Trust yourself. Trust yourself. And I think it's more frustrating to realize you changed your answer off the right answer than getting it wrong.
Yeah.
And a lot of, like, so many times I talk to students and they're like, I had it right, and then I thought I made this mistake, and I was like, why'd you think you made that mistake? And they're like, I don't know, I just thought there was an extra trick. And it's like, no, you had it right. So trust yourself unless you see an obvious mistake. Like that. And it's just like, oh, I just got the order wrong. Also, making sure we label things becomes really nice as well. So that way, because like, if I just wrote 26, 30, 23, then I'd have to like re-remember, like, wait, what was the 26 again? Speaking of iron and ions, let's talk about effective nuclear charge, ionization energy, and electron affinity. Yes? Okay. Wait, did you have 2.2 number 16? Or was that somebody else? That was you. Okay. Is it okay if we do this one first?
Yeah, I just have to go with 3. So
What time is it?
it's 2:47.
Let's do 2.2 number 16, and then we'll jump to that one. Unless 2.2 number 16 is really long. I don't think
it is. I think I just made a silly mistake.
What is 2.2 number 16? And then we'll talk about some concepts.
Calculate the wavelength in micrometers of a photon that is
Ooh. Sorry, I did micromolarity instead of micrometers.
of a photon that is produced when electron in a hydrogen atom drops from n equals 6 to n equals 4.
Yeah, that's a good one.
Okay. What's the implied information?
Rydberg.
Right. Delta E equals negative Z squared over H, 1 over 4 squared minus 1 over 6 squared. Right? As soon as we see a problem like in this quarter, and this is again like just a categorization thing of how we think about it stuff, whenever I see two n values, Rydberg equation. Right? It's given on the equation sheet. It's the only thing that has two n values, probably a Rydberg equation. So I can, since it tells me it's hydrogen, I know that's equal to 1. I know the Rydberg constant is 2.18 times 10 to the minus 18. So I can solve for my energy change in the atom. It's going from 6 to 4, so I'm expecting this to end up being a negative energy because it's dropping. And it's asking for an answer in micrometers, so I'm guessing it's going to be like a couple hundred micrometers. Like it's asking for a weird unit. So why didn't it ask for nanometers? Probably because nanometers would be a strange answer, and micrometers is going to be more sensible. Let's go ahead and do 16 inverse minus -6 inverse times 2.18 times 10 to the minus 18.
Why isn't that negative? The 2.18.
Oh, it should be, sorry,
Okay.
negative. Because I just dropped my negative when I was bringing things down.
Because sometimes it isn't negative, right? Like when it's like the absolute value of it. So
Yeah, and I'm going to do the absolute value step next. Whenever we do the delta E, there's always a negative out front.
Okay.
And then we've got 1/16 minus 136 times that. My delta E is going to end up being negative 7.5. I'm going to round a bit, 7 times 10 to the minus 20 joules. Again, because this Rydberg constant has units of joules. And then to relate my change in energy of the atom to the energy of a photon, I'm going to have my energy of photon equal to the absolute value of my change in energy of the atom. And so that's going to get me hc over lambda is equal to positive 7.57 times 10 to the minus 20. And then my rearrangement, for some reason people love to divide hc over and leave 1 over lambda. I'm like, no, just flip the other things, right? I'm going to bring my energy down, my lambda over, so I've got lambda is equal to 7.57 times 10 to the minus 20. And I'm going to solve that. Inverse times 6.626 times 10 to the negative 34 times 2.99 times 10 to the 8th. And wouldn't you know, 2.61 times 10 to the minus 6 meters. Unless I punch something into my calculator wrong. Is that what you got?
Yeah.
Yeah?
Yeah.
Anyone else following along? Okay. And look at that. At the 10 to the minus 6, we've gotten okay with our unit conversions. I can just say 2.61 micrometers.
I have a question.
Yeah.
On the equation sheet, I see 3 different kinds of formulas that are like this one. I'm just curious.
Which equation sheet are you looking at?
This one, and this one. I'm just curious where each of these are applicable. So, like, why would I want to have that instead of this?
Is that the old version of the equation sheet?
Yeah,
Yeah, you got an old version of the equation sheet.
Huh.
So yeah,
That would explain a little bit of my issues.
we dropped the 1 over lambda equation because it causes more confusion. 1 over lambda is valid, and so the way that 1 over lambda equation is essentially doing this HC dividing over step for you, but then you have like a different Rydberg constant. Here, look.
Or, yeah, do we have extras?
Take that one.
Thank you.
Yeah. And I think I've got a whole pile of extras right here too. Yeah, I've got a whole pile of extras.
Awesome.
Yeah, so that is, we've tried to simplify the equation sheet some, so we got rid of that 1 over lambda one. We can derive the 1 over lambda equation if we need to. I used to teach it because sometimes it's a nice shortcut, but it's supposed to be a shortcut and it really confuses people because they think it's like 2 different equations when it's like, no, it's the same thing just written in different units.
Gotcha. So there's only one Rydberg equation that we are expected to maybe use.
Yeah.
Sure. Cool.
And then the different versions of the Rydberg equation, like essentially that other version of the Rydberg equation is like, oh, we converted everything to meters for you already.
Gotcha.
And so it's just like supposed to save you math steps, but it confused people more than it saved them math steps.
Sure.
Good on that question.
Is that supposed to be, is it a B or a 6? Or is this N equals
N equals
B?
6.
Okay,
Sorry,
I
that's
was
a 6.
trying to figure out what happened there.
I was writing sideways a little bit. Does that still look like a B or is that a 6?
No, that's fine.
Oh, that's the B. Okay, that's, yeah, 6 squared.
And I also have a different question, but I could stay like maybe afterwards, but like I might need a little help like actually getting all of that to work in one step on this kind of calculator. Like I usually have
Oh, I
to,
don't
like,
do it in one step.
You don't?
No,
So
no,
you
no.
actually do have to like write down each different.
Absolutely,
Like,
and that's
1 over
that's
4?
what I
Sure.
think one of the benefits of using those calculators is because it slows you down and makes so you're kind of like writing down your steps so you can follow
Sure.
your work.
So you want to do 1 over 4 squared alone, so you can write it down and then.
Yeah.
Okay, gotcha.
Once I put it all together.
You are, and I forgot to
Stuff.
update this.
Gotcha. Okay.
Okay, let's go ahead and talk about effective nuclear charge, how it relates to ionization energy and electron affinity. And we're going to start, and I always think this is the best way to start when we're having these conceptual discussions, so we're going to start with defining each of these things. So ionization energy is the energy to remove an electron from a neutral atom. I should be more specific. It's not just any electron, it's a valence electron. The part of in the gas state is important because that means we're not going to have to worry about any other energetic interactions of that atom with other atoms. So it's really just that atom sitting by itself, how much energy does it take to knock away an electron? Electron affinity is ooh, that E went weird. That says shell. That word got weird. Shell. And get in the gas state so we don't have to worry about other energetic interactions. So energy to remove an electron from a neutral atom, energy to add an electron to a neutral atom, looking at the valence shell. We're not going to throw, technically there's some really cool spectroscopy you can do where you knock electrons out of the core. You can do core electron spectroscopy with X-ray radiation. It's really cool, but it's really weird and we're not doing that. So we're just looking at the valence shell. We're removing electrons or adding electrons to the valence shell. Effective nuclear charge. Great. So that's the effective force the nucleus has on valence electrons, how much attractive. I could put attractive force here. Right, because the nucleus attracts electrons in, and it's not, actually it is exactly equal to Z minus sigma. The part that's approximate is I've been telling you sigma is approximately equal to the number of core electrons. It's not exactly equal to the number of core electrons, but it's pretty close. You bet, see ya. So, some of this has like really nice direct kind of relationships. Hey, come on, there's a chair right there.
Thank you.
Some of this has some really nice direct comparisons. Ionization energy is the energy to remove an electron. Effective nuclear charge is how much force the electrons are feeling pulled towards the nucleus. So those two things are like opposites of each other. If your effective nuclear charge goes up, your ionization, actually they're directly related to each other. If your if your effective nuclear charge goes up, your ionization energy should go up, right? And so the idea here is, and we can draw all kinds of pictures to go with this. These are like the words, the vocabulary we're all studying. And then we have to have the kind of conceptual understanding of it as well. Here's my nucleus, here's my inner, here's my outer. I'm going to change the colors to make it more dramatic. Here's my outer shell. There's an electron here, and so my shielding is going to be due to the core electrons here, and then I'm going to say, okay, the nucleus has some charge associated with it, and then how hard is it to remove that electron? Well, the more attracted that electron is to the nucleus, in spite of that shielding, effective nuclear charge, the more energy it takes to remove the electron. So I can see that ionization energy and effective nuclear charge directly relate to each other. I see the same thing with radius, right? Actually the radius is the opposite one, right? The more effective nuclear charge you have, the tighter things are held in, the smaller the radius becomes. So we have an inverse relationship there. We have a direct relationship between ionization energy and effective nuclear charge. The one that goes a little bit weird is electron affinity. Because electron affinity, you can imagine if you've got a large effective nuclear charge, you would pull electrons towards you better. But that's not the only thing that dictates electron affinity, and that's where this one, whenever we talked about this one, I almost wrote strong strand. So, ionization energy and radius were both strong trends. They tracked really well with the periodic table. Electron affinity, it's kind of a so-so trend. And the reason electron affinity becomes weird like that is because electron affinity has these other aspects to it as well. It's like how full is the valence, how much space is there around the nucleus, right? If you look at the periodic table, if you're looking at the noble gases, The noble gases have no electron affinity, even though they have some of the highest effective nuclear charges, because they have no more space left in their shells. But if you look at something like fluorine, chlorine, bromine, iodine, those halogens that are one row over to the noble gases, they've got small radius, they've got that high effective nuclear charge because they've got their core electrons, they've got an opening in their valence shell, and they got a lot of protons. So they have that high effective nuclear charge. They pull electrons towards them really well, but only one, because there's only one space in the valence shell.
So yesterday when you were saying in class of low ionization and small electron affinity, so those are related, but
well, so that was looking at the properties of an atom, right? So any atom on the periodic table, see, I have a good class. Any atom on the periodic table, we can look at like oxygen and say, what's its ionization energy? Well, what's its radius? What's its ionization energy? What's its electron affinity? What's its electronegativity? What's its Z effective? Right? We can talk about those 5 things for any atom on the periodic table. And then we can say, okay, what are the consequences of those properties? So when we were yesterday in class, when we were saying, okay, we're going to look at fluorine. What's its what's its ionization energy? What's its electron affinity? And from its ionization energy and electron affinity, what can we predict about it?
from fluorine,
From fluorine.
that's going to be really hard to take off electrons.
It's got a really large ionization energy. It's really hard to remove electrons from it. Its electron affinity? Strong electron affinity. It's going to pull electrons. It's not going to lose electrons, and it's going to pull electrons towards it. That's what allowed us to predict that fluorine forms a -1 charge. And same thing with chlorine, bromine, and iodine. All of those things that have that like one more electron would fill their shell. They have that high electron affinity because of that. They all end up with -1 ions. Lithium, sodium, potassium, rubidium. Each of those, we can talk about the ionization energy and electron affinity of each of them. We can also talk about the effective nuclear charge of each of them. They all have pretty bad effective nuclear charge.
So we can talk about all of them in every atom, but it's just when it comes to like comparing them.
Yeah.
Like the consequences of each is different.
Yes, right? So it's the consequences of each of them. And they kind of reinforce each other. You notice it's like when you looked at fluorine, it was like it doesn't want to lose electrons and it wants to gain electrons. It's reinforcing ideas. When you look at sodium, it doesn't want to gain electrons. It's easy to lose electrons. These things reinforce each other in terms of their behavior.
Okay, so that's what you meant in the question from yesterday, right?
Yeah.
Okay.
So it was like small, small or big, big. We didn't really look at cases where we have small, big, because that doesn't really happen. And that doesn't really happen because of the way that all of these things relate to each other, kind of through effective nuclear charge. We're just doing like a broad conceptual understanding of these things. There was no like specific question we were working on.
Could we, or rather, do you have an example of a possible question that involves Z effective, or do we not have to worry about that for this upcoming midterm?
You do have to worry about for this upcoming midterm. We talked about it like last week, and so it's fair game.
Sure. What's an example?
I mean, what kind of questions can I do for this? It's going to be mostly conceptual explanation, right? Like I could do problems where it's like calculate the Z effective for this thing or that thing, but that's just like counting core electrons and valence electrons, and I don't know if that's like a very robust question.
Sure.
So it would probably be like a really conceptual question. I don't have one off the top of my head.
That's all right.
Okay.
Yeah, in that case, it's simply just doing atomic, like the atomic number minus, what does that sign mean again?
Sigma, the underline was to make it more dramatic. So sigma is shielding.
Yeah.
And generally, shielding, we don't know what, like shielding can have a lot of values. For us, this quarter, we've said it's approximately equal to the number of core electrons. It's an oversimplification, but it's a pretty good starting spot.
Gotcha. Thank you.
So we wouldn't have like that equation to do on the exam. It's just like conceptual, like knowing the definition of it.
I mean, you could, right? I could be like, hey, compare, like, I can imagine making a question where I'm like, look at the behavior of these 3 atoms. Explain how the behavior is similar or different. Make sure you refer to the effective nuclear charge for each atom/ion as you go.
But that involves more like the definition.
Again,
of it.
right.
Like, we don't have to do it.
Well, like, if you would still need to be able to talk about this and kind of get some numerical value for it, for like comparison.
It's like a guessing, right? Because I don't know how to calculate the core, or like how you would do that.
Oh, the core?
Yeah.
Maybe we should do that for a couple. Question before we do that?
So is there a relationship between the effective nuclear charge and the energy affinity?
Electron affinity?
Yeah.
Roughly, but not perfectly. Usually things with high, and that's because of the way that electron affinity has more than just attractive forces playing in it. Right? The reason ionization energy works pretty well for most of the cases we look at is because it's looking at attractive energy, and it's like the opposite of attractive energy, is how much energy to stop the attraction. This one is how much attractive energy and how full is the shell. Right? So things with large effective nuclear charge generally have large electron affinity as long as they have space in their shell. And so that's an important distinction because the noble gases don't have any electron affinity because they don't have any space in their shells. The halogens, fluorine, chlorine, bromine, iodine, they have high electron affinity because they've got that high effective nuclear charge and space in their shell. Oxygen, sulfur, selenium, same situation. They tend to attract 2 electrons because they have pretty high effective nuclear charge and they have 2 spaces in their shell. So that's where it's like a strong trend versus a so-so trend, is because this one is very much energy related till you start trying to take away core electrons and then it gets weird again. But generally when we're trying to take away electrons, we're just looking at like the first ionization energy. When we're trying to add electrons, it's like, ooh, there's a couple, it's more than just the attractive energy. It's also valence space.
Yeah, I guess I was just confused on the question yesterday, like how to answer it, where it was like ionization energy and electron affinity, like why are they like not opposites?
Oh, yeah. So, and that's because, yeah, absolutely. Do you remember what you put?
I remember I like gave the definitions, but I was struggling to come up with like the analogy, like how are they not? Like they're kind of like opposite in definition.
It's kind of like, imagine you're on the first floor of a building, and you're either going to the basement or you're going to the second floor. That's not opposites of each other, even though they're going different directions. Going to the second floor and back to the first floor would be like opposite. Going from the first floor to the basement is not the opposite of going to the second floor. You're going different directions, but where you start matters. Does that analogy make sense?
Yeah, so it's like the opposite of electron affinity. It wouldn't be going to the basement. It would go like up and then down.
Yeah,
Okay.
right? So electron affinity would be you're starting on the first floor, gaining an electron, you're going up to the second floor.
Mm-hmm.
Opposite of that would be starting at the second floor, going down to the first floor. Does that work? Okay. I've never thought of that analogy before. Was that an okay analogy?
Yeah.
Okay. Because like the thing I did in class yesterday, which made total sense to me, I was like, let me just write the electron configurations. Clearly it's different. But like, that doesn't work for everybody. I kind of like the basement second floor thing. I'll have to think about it more. Other questions about this general idea?
Yeah, so
Okay.
when the energy release is high, when you remove an electron, that means
careful. When we remove an electron, we have to put a lot of energy in to make that happen. Right? The electron is being attracted to the nucleus, and we have to put force in to push it away.
okay. So then, why is energy released when you add an electron?
So this is kind of a weird thing to think about, right? So essentially, Here's the way that I think about it, is like you have this electron zipping around, and it's got energy, and then when it comes to the nucleus slows it down, and that breaking speed essentially releases energy. I never have a good way to explain why trapping an electron releases energy. But I can make sense of ionization energy. It takes energy to knock an electron away. And the truth of the matter is, and we haven't looked at this picture yet, but essentially when we look at the attractive force of a nucleus, it's an energy well. If you remember when we were doing our hydrogen atom, it was like a negative 13.6 electron volts, right? It was a negative energy. That's because it's a well. So when an electron is kind of floating around, not attracted to anything, when it comes close to a nucleus, it falls into that well, and essentially that loss of energy of the electron is just shot out to the universe, usually as like photons or some other like energetic source.
Okay. So.
But like, it's not something that even in my head sits totally like perfectly.
Right. Okay. So when a lot of energy is released, when it's added, that means it has a low electron.
When a lot of energy is released, that means that's a high electron affinity. It pulled the electron towards it really well.
Okay.
Right? So the energy released, like think about this, like if there's a lot of energy released as that electron is attracted, I'm going to have to put that amount of energy back in to push the electron away. So that means that it's going to hold on to the electron really well. It's going to have that high electron affinity, a large negative value. And I think that's the other thing that's tricky with the wording is people like to say big value, small value. And it's like a big number, small number. But some people consider like negative a billion a really small number because it's like really negative. But it's a large negative number versus a small negative number. A large positive number versus a small positive number versus a large positive number. So when we say big and small, we have to be really careful that we're talking. And you notice I did that in the question yesterday where I was like, ionization energy is a large positive value, and electron affinity is a small but negative value.
So it wouldn't be a positive value for electron affinity?
The only times we see positive electron affinities are things that essentially we have to force electrons to stay around them, like the noble gases. So if you look at the noble gases, I say they don't have any electron affinity. I say that what I mean is to say they don't attract electrons. If you've got like a helium and you want to put an electron next to it, you have to constantly put energy in to hold that electron next to it. You stop putting that energy in, the electron is going to fly away. So that's what happens when you have that positive electron affinity.
Okay.
And there are a few other cases besides the noble gases where we see that, but it's pretty uncommon. Some transition metals, like the transition metals sometimes do it. I mean, even like sodium has a negative electron affinity. It's almost zero, but it still has a negative value. Some of the transition metals are positive. I think there's one in the P group, but it's like in a really low row, has a positive value. Most of the noble gases have positive values, but positive values are uncommon. Other questions about this, or are we ready to move on? Do we have other things to move on to? Those of you who've shown up, questions.
You can go first.
Okay, so right now what I'm going to do is I'm going to erase this and let's get a new list of questions. So these are the questions we've gone over already. I'm happy to go over them again, of course, especially since some of you just showed up at the hour. But let's see what other questions we have to go over.
I have a question kind of about, like, depending on the question. So when it asks for the energy in joules for an electron in a hydrogen atom when it relaxes. So would that...
Which problem is this?
This is 2.29.
What question do you have?
My questions, I'm getting them. So I'm in the workshop,
Uh-huh.
and I have just a few questions from that.
The mock midterm?
Yeah.
Yeah.
Like have questions about like drawing energy diagrams, and then also just kind of finding like the protons, neutrons, and electrons from a given element.
Okay. Are those the two main things?
Yeah, that's.
And we can look at that sample exam as well.
Okay, sounds good.
I also have a few questions. From 2.1, if possible.
Yeah.
Generally, frequency, wavelength problems with combined energy.
Do you have some specific numbers? From
Yeah, I have
2.1?
number 11 and 12.
Okay. Yeah, take it. And do you know what questions you already have? I'm just making a new list since a bunch of people just got here at the hour.
Yeah, I have quiz. It's one of the quiz questions.
In the meantime, let's start with 2.2. We'll do 2.2, 2.1, then we'll look at the quiz, and then we'll get to the worksheet if you don't mind that waiting
Yeah,
a little bit
that's fine.
since that's going to be okay. So let's look at 2.2, number 9. What is 2.2, number 9?
It says, what is the energy in joules for an electron in a hydrogen atom when it relaxes from N2 to N1?
Wait, n equals 2?
2 N equals 1.
Can you read that again? What is the change?
Change in energy.
I just missed the word change, and so I was like, wait, that doesn't make sense to me.
Yeah.
Change in energy. 2 n values, what equation are we going to use? Rydberg, right? So Rydberg equation, this will also touch towards writing energy diagrams a little bit. Rydberg equation tells us the change in energy of an atom is going to be related to the attractive force of that nucleus times the Rydberg constant times 1 over n final squared minus 1 over n initial squared. And I always think about it, I'm pretty sure the only energy diagram we've really done is this thing. Now this is a pretty easy one to do because I don't even need to draw the 3 levels because this problem is only asking me to look at n1 to n, or n2 to n1. But I like to draw it to get a sense of what's going on. So here I can see that my n value is going down. My atom is going to be losing energy. It's going to go from something more positive to something more negative. So I should see some energy lost from this. I should end up with a negative energy of the atom. So let's go ahead and calculate it and see what we get. Okay, so we got our change in energy of the atom is equal to -1 squared times 2.18 times 10 to the minus 18 joules. My 18 looks a little funny, sorry about that. 1 over 1 squared minus 1 over 2 squared. That's going to be 0.75 times 2.18. Right, because it's -2.18 times 10 to the minus 18. This is going to be -1 minus 0.25 because it's 1/4. That's going to be 0.75. So I'm going to have 2.18 times 10 to the minus 18 times 0.75. And I'm going to get a value of -1.635 times 10 to the minus 18. Ooh, my 18 looks weird again. Can't draw 18s with this pen for some reason. 18 joules.
So since it relaxes, that means that it would be like a negative number? Or does
Yeah, well there's a couple things that relaxes means, right? So relaxing means that you're going from a higher energy to a lower energy. We can also see that because we're going from n equals 2 to n equals 1. And I still like to draw the energy diagram so I can kind of like have this visual picture of it's going down in energy.
Okay. And then when it's excited, it's going from
A lower to a higher.
Okay.
Relaxation now, this was trying to not, this was an earlier question that was like, I don't want to think too much about like photons and the lambdas and stuff like that. Typically, when an atom relaxes, there's many different ways it can happen. In this class, we've mostly been talking about relaxation with a photon emission. It's not the only way that relaxation happens, but for us in this class, that's what we've been talking about, is photon emission. Yeah. Okay, did you find your question?
Oh yeah, it was one number 3. Oh, that's already up there.
Okay, we can look
Did
at
you
it
already
again,
do
though.
it?
Yeah, we can look at it again, though.
I can watch the video too.
Yeah, we'll get it at the end. I don't mind redoing things. But let's keep going.
Number 6 was quiz 2 number 6 was
Quiz 2 number 6 as well?
Yeah.
Okay. Before we do that, let's go ahead and look at 2.1 number 11 and 12. And then we'll look at some of those worksheets from the workshop worksheets. What do you have for 2.1 number 11?
2.9 number 11 says the wavelength in micro or of a photon, if 10 to the 20 of these photons combined have an energy of 1 joule.
It says 1.00 joules, yes?
Yeah, 1.00.
Okay. And it says total energy?
The wavelength of a photon, if 10 to the 20 of these photons combined have an energy of 1.
Okay, combined. Some way that says this is all together. Okay, so in our implied energy, in our applied equation, what's being implied? There's kind of two different things that are being implied. We've got some energy with a number of photons. We've got a wavelength and some energy. So one thing is the energy of a photon is equal to hc over lambda, since it's asking about wavelength. We have to keep in mind, this is one thing that people really lose track of. This equation is for one photon energy. Right? And that is really an implied piece of information. So when we calculate the energy of a photon, right, we always say it's the energy of a photon. Sometimes not realizing that the of a photon means it's a single photon. So if I want to get the energy of many of these photons together, let's say I want to get the energy of 2 of these photons, what would I do to get the energy of 2 photons together?
Multiply by 2.
What if I wanted to get 50 photons together?
Multiply by that.
What if I wanted to get 10 to the 20 photons together?
Multiply by 10 to the 20.
Right, so the other implied equation is that the total energy is the number of photons times the energy of the photons. Right, we can do that. I've never written that equation down. It's kind of one of those things that you can just logic through. Like if I put 500 photons together, it's that energy times 500. Sure. And now when I have these two equations, I'm like, oh, look. Right, I have the total energy is 1.00. I have the number of photons is 10 to the 20. And I've got the energy of the photon. I can just plug that in. It's hc over lambda. I can just solve for lambda now. Again, recognizing those kind of implied ideas, can you think through the things that aren't being explicitly told, becomes this important piece. So I can actually rearrange this pretty easily. And I can probably solve for wavelength. Does it tell us what units it wants the wavelength in?
I don't believe so. It doesn't say anything next to the evaluate.
Okay. So we're going to do 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8th times 10 to the 20 divided by 1. And I get 19.8 micrometers. Oh yeah, it's in micrometers. It says it in the problem.
Oh, I didn't see that. No.
Yeah. No, that's okay. I forgot too. But then I got an answer, and I was like, oh, it's close to micrometers. I should probably put the answer in micrometers.
Oh, yeah.
I got 1.98 times 10 to the minus 5 meters. and I do my trick
In
for
that case,
converting,
yeah.
19.8 times 10 to the minus 6 meters is 19.8 micrometers.
Sure. Okay.
Number 12?
Yeah, this one has to do with frequency.
Okay.
The frequency.
Sorry, hold on.
Well,
So-
hold on, before we move on, yeah.
So you know it's in meters because the speed of light is in meters?
Yes, right, so unit analysis, let's put the units in real quick. This energy is in joules, speed of light is meters per a second, Planck's constant is joules seconds, seconds cancels out, joules cancels out, I'm left with meters.
Yeah. Cool.
Other questions before we go to number 12? Okay. Let's take a look at number 12.
For sure.
Twelve.
12. The frequency in hertz of a photon, if 10 to the 20 of these photons combined have an energy of 1 joule.
Oh, I shouldn't have erased all of that work we just did because they're related to each other.
Is it as simple as changing the variable? Or is it a different
Yeah.
equation?
No, it's honestly like I could have used the wavelength from the last one.
Yeah.
Right. Since it's the same numbers, I can just use nu lambda equals c, plug in the lambda I calculated from the last problem, solve for nu.
Okay, gotcha. Yeah.
Right, so just a little bit of a rearrangement. We could have done it the same way, right? I could have done the same thing. I could have done the energy of a photon equals h nu, energy total equals number of photons times energy of photons, and then I would just have 1 is equal to 10 to the 20 times h nu, and same thing, right? I just use h nu instead of hc over lambda, those two equations, right? I could have used either one. But since we already had those numbers used, it would have been easier if I just used my wavelength answer from the last one,
Sure.
plugged it in there.
We don't have to go through the entire process, though.
No, I think that
That's good.
hopefully clears it up, yeah? Ready for some workshop questions? Let's take a look at some workshop questions.
After the workshop questions, can we also look at, like the most recent workshop, like how to draw the Lewis structures?
Yeah. Did you do that in workshop last night or?
No, this was from our last class.
From
This
class,
was-
okay. You
yeah.
said from our most recent workshop, and I was like,
Oh.
workshop or class?
Yeah,
We can
my
look at
bad.
that. We're also, that's not going to be on the exam, and we're going to talk more about it next week as well.
Oh,
But we can talk about it now too. Like,
okay.
the more we talk about it, the better. But let's start
we
with.
can focus on the other stuff.
Yeah, let's
first.
focus on the other stuff. But I still think like, the earlier we see things, the less confused we get by it.
Yeah,
I just know a lot of people are really exam focused right now.
yeah. Okay.
Yeah.
I think it's gonna rain like after 5.
Yeah. Oh yeah, did they change when it's gonna rain yet? Okay, while you're getting your questions, I'm gonna check the weather again. I'm gonna see how drenched I'm gonna get when I'm biking home.
Okay, so, oh wait, you can go first.
I had a question about like how the in-person midterm would work.
Mm-hmm.
So you said there's like the Scantron,
Uh-huh.
and then will we also have like a sheet like where we have to like show our work? and stuff,
Scratch
or-
paper, yeah,
Yeah,
like,
okay.
yeah. I always encourage the more you show your work, the more partial credit you're likely to get.
Okay.
There's a Scantron and a writing section, or
Yeah.
just?
And I provide the Scantron, so you don't need to worry about that. There's a whole really great Scantron system called the Kindi that I really like, and we use that.
Okay,
'Kay.
so there's one question, and it's just how many protons, electrons, and neutrons are present in this right here. It's like 78 SR 3 plus.
Okay. Can you find SR on the periodic table?
Yes.
Do you know the name of SR?
Uh,
Strontium.
Strontium?
Yeah.
I did not know that.
We will learn it. So we want to find the number of protons.
Okay, I found it.
What's its atomic number?
38.
That's the number of protons.
Oh, 87.62.
That's the molecular weight. It's just the number at the top of the box is the number of protons.
Oh, 2, sorry.
Wait, say again?
2? Wait,
Looking at strontium.
am I looking at the right one?
Strontium, 38.
Yeah, I said 38.
Oh, yeah. That's, yeah. And then you said 2.
Oh, sorry.
No, that's okay, yeah. So I wrote 38 because you said 38, and then you were saying a different number, and I got confused.
Oh, okay, my bad.
No worries, okay. So that's our number of protons. Then our number of neutrons. 70, ooh, I'm gonna write my 7 weird. I almost wrote a 2. So our number, that 78 is gonna be the number of protons plus the number of neutrons, which means I can solve for my number of neutrons just by doing 78 minus 38, 40. And then my number of electrons is going to be, if it was neutral, it would be 38. Now, am I going to add more electrons in or take electrons away? If it's a positive ion.
You're gonna add.
Take more.
Are electrons positive or negative?
They're negative.
Electrons are negative. So if I want to get a positive charge, I need to take electrons away. So I'm going to take 3 electrons away to make it so I have a +3 charge on the ion. That's going to be 35 electrons. So the 3 pieces that we need to know, the letters in the middle give us the symbol, that gives us the number of protons. The number at the top left has the fancy word number of nucleons. It's a fancy way of saying number of things in the nucleus, which is protons plus neutrons is nucleons. So since I've got the symbol, I can figure out my Z. Since I know my number of nucleons, I can figure out my number of protons, because my protons and my neutrons need to add up to 78. Then my charge of ion, top right, tells me if I need extra electrons or less electrons from the neutral atom.
Okay.
Okay?
Okay, there's.
Should I give you one to try?
Sure.
Let's see, can I remember one? Let's do, let's do a fun one. Let's do silver plus, let's do silver 106. I'm going to give you a minute to work on it. I just made this up. I don't even know if that's a stable isotope of silver. After you have answers, show them to each other, see if you agree with each other. I don't feel like checking if it. I'm really curious if I made up a stable isotope of silver. We haven't talked about, nor are we gonna talk about what makes different isotopes stable and unstable. That's more nuclear physics. What'd you get?
I can't do math in my head, but.
Let's get the number of protons.
Protons, it's 47.
Number of electrons.
Let me do the math.
Oh, electrons should be easy. You don't need a calculator for that one. If it's +1, it's just one less of that.
Oh, so okay, so 46.
Number of neutrons is the tricky one, where we have to do 106 minus 47, which is going to be 959.
It's 59.
And then just make sure we put those in the right order in the right boxes.
Okay.
That's a
He's
problem.
gone now.
Yeah, he left. But that's why someone got it wrong on quiz 1, was they just put them in the wrong order.
I keep getting 61. It's 108 minus 47, right?
That's a 106.
106?
I did a different isotope.
Yeah, you did.
So I did the 106 isotope.
Oh, okay.
Yeah, 108 is the more common isotope, and if you're looking at the molecular weight on the periodic table of that 107.87, the atomic mass is the average of all of the isotopes.
Gotcha. So in order to find neutrons, you have to look at that top left
You
number.
have to look at the top left number for a particular isotope.
A little bit unrelated. So the for Planck's constant in joule seconds,
Yeah.
what is a joule second? Is it joules per second?
No, it's joules times seconds.
Okay.
So there's two different ways to think about it, and I've struggled with this one as well. And it's really, when you look at how Planck came up with his equation, he just said, hey, h is some proportionality constant between energy and frequency. Since energy is in units of joules and frequency is inverse seconds, my constant must be joule seconds. Right? Just through like the logical process, this has to, in order for the units to work out, that has to be joule seconds. In terms of its physical interpretation, it's like an energy flow idea. It's like energy, it's energy and time being related to each other. It's kind of weird. For the most part, it's like most other proportionality constants, like epsilon. What does, when we look at the units for epsilon, do you remember what the units for epsilon are? Molar absorptivity?
-1 centimeters.
Yeah. It's inverse molarity, inverse centimeter. Does that unit really make sense? No, but when we look at the equation of A equals epsilon BC, if our C is in molarity and our path length is in centimeters and our A is in no units, then my epsilon has to be in units of inverse centimeters molarity in order for the units to work out properly. So the units end up just being those necessary to make it work out. There is deeper physical interpretations that are possible, but I struggle with them.
So is
I
it
haven't looked
helpful
into it enough.
to write out joule seconds when you're solving so that you can see if they cancel out?
Yeah.
Okay.
Yeah. Right. So you can see seconds cancels out, and now you're just joules to joules. Same thing happens with this Planck's constant times the speed of light. You end up with joules meters, which doesn't make sense until you divide by wavelength, and joules cancels out, and you just get, or you divide by wavelength, so meters cancels out, and you just get energy equals joules. Okay. After that, a brief aside. Was there another workshop question you wanted to
Yeah,
ask?
I have one more. The question is, rank the following elements from least to most electronegative and explain your reasoning.
Ooh.
And then the elements are PCI, I think that's an I. No, that's an L. CL and then F.
PCL?
Yeah, it goes PCLF.
Okay. Phosphorus, chlorine, fluorine. We're going to look at the periodic table. Okay, do we know which one is the most electronegative? Fluorine's most electronegative. So are we listing least to most or most to least?
I think it was least to most. Yeah.
Least to most, fluorine is definitely going to be the last one. Fluorine is going to have the biggest electronegativity. Everything is going to be smaller than that. Chlorine versus phosphorus. Okay, so all we have to figure out is which one's going to be more electronegative, chlorine or phosphorus. Look at the periodic table.
I found phosphorus.
Where's chlorine?
This is the right of it.
It's right below it.
Okay, so which one's more electronegative, chlorine or phosphorus? So it follows the same kind of trend as ionization energy and electron affinity, where fluorine is the most electronegative, oxygen's a second, chlorine is a really close third, and as you move across the table, it gets less and less and less and less.
Okay.
But it's really, what's that?
Which direction across?
As you go from top right to bottom
So
left.
it's the same as atomic radius?
The opposite of atomic radius, because fluorine is the biggest electron
because it would
negativity.
go up
Yeah.
instead of down.
Yeah, so, and
So
it's
when
go
you
ahead.
start in the top left, it goes from most electronegative,
Ooh.
and then
top left. Yes. Wait, no, top
Right,
right.
no,
Top
yes.
right. Top right.
Top right. That's where fluorine is.
so top right is the most, and then as you go.
Yeah.
Top left is
Okay.
the least.
Okay.
Yeah, and we have to be careful because that kind of general trend really only works for a short period for electronegativity, right? Fluorine, as soon as you get to like arsenic, like you're pretty much out of electronegativity. Nothing that far away from the valence shell, from having a closed valence shell, really attracts electrons to it very well. So it's not a great kind of like you can follow that trend directly across the entire periodic table. It's like works well in that little top right region, and then it works okay in the bottom left region, but across the middle there's a lot of kind of hiccups to it.
Okay.
But this is all in the top right, so this is going to work pretty well. Chlorine is next, phosphorus is least. Which is funny because it means it was already in order.
Oh yeah.
Yeah.
But now we have to justify why that's the order.
Yeah.
So when we when we look at electronegativity, we're looking at this combination of how well does something attract electrons to it, electron affinity, and how difficult is it to take electrons away from it, ionization energy, compared to other things around it. So fluorine is the most electronegative and everything is relative to fluorine. So I say, okay, fluorine comes towards something. How well does fluorine pull electrons away from it? So fluorine has really high electron affinity, so it's going to pull electrons pretty well. It has high electron affinity because it has that small radius and that one valence in its shell. So that one opening in its valence shell. So if it had one more electron, it would be satisfied. So it really wants that one more electron. It has really high affinity for one more electron. So that's the combination of ideas that explain why fluorine has that really high electronegativity. It really wants to pull electrons away from things.
Okay.
Now, if you put fluorine next to chlorine, you're probably not going to form F- and Cl+, because their electronegativities are pretty similar to each other. But if you put chlorine next to something else, chlorine has pretty high electronegativity. So you might form like a chlorine-fluorine covalent bond because they're both pulling electrons away from things. And so that's what we kind of look at for that explanation. We're looking at ionization energy and electron affinity to explain electronegativity. I'm going to throw radius in there because it relates to them as well. Z effective because that relates to them as well. But you notice we kind of start running ourselves in circles because it's like ionization energy relates to electronegativity, which relates to electron affinity, which relates to Z effective, which relates to radius, which relates to ionization energy, which relates to, and you're just kind of running, and it's like all of the ideas relate to each other.
Mm-hmm. All right. Sounds good.
Okay. Anything else from the workshop?
That was kind of everything.
Okay.
It was mostly just like the more conceptual
Yeah.
questions.
And also, I think you weren't here, but we did a pretty long conceptual conversation about ionization energy and electron affinity that I recorded.
Okay, I can
So
go
you
back
can
and
look at
watch
that too.
Okay.
Let's do number 6 before number 3, because again, we've got number 3 recorded. I'll do it again, but let's do number 6 first.
Shouldn't Arthur?
Yeah.
How long are you gonna possibly stay afterwards? Just because I have a personal question.
I can stay afterwards for a
Awesome.
bit. Yeah.
It won't take more than like 5 minutes or so.
Great. Yeah. So we're looking at quiz 2.
Thank you.
You bet. See ya. Number 6. Can you go ahead and tell me what that question was?
If I haven't taken the quiz, should I just not be here for this, or is my
Wait, have you not taken the quiz?
Yeah, I'm the person that was meeting you today.
Oh.
About making everything up.
Yeah.
So should I go?
Yeah, just for a sec. Yeah. Don't watch the. Well, yeah, we have to have a longer conversation.
Yeah,
but
so
like...
I can always come back another time. If
No. Hang on. No, we'll talk now.
Okay.
But yeah, we'll have to talk about some details. But just
I'll just come back at the end of office hours.
Yeah, that sounds great. Which is pretty soon, yeah.
Yeah,
It's pretty soon, like 10 minutes.
Okay.
I want it to be 5 minutes. Okay, no, go ahead.
It was how many photons emitted each second by a 10 milliwatt 1.086 times 10 to the third nanometer light source.
In 1 second?
Each second, yeah.
What was that energy of the laser?
It was so 10 milliwatt 1.086 times 10 to the third nanometers.
Sorry, what was the nanometers again?
1.086 times 10 to the third.
Nanometers?
Yes.
Okay. So, how many photons emitted in 1 second by a blah, 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 blah. Okay, so there's a couple different things. One is, does it also give you the hint that 1 watt equals 1 joule per second?
No, but I think we knew it from the homework.
Yeah, it was in the homework problems. Okay. So, I thought I included that on there, but I should have. Okay. Just because, like, that's a physics thing. But in any case, so we can have a couple things we need to know. We've got photons. We've got some energy. We're going to have energy of photon is hc over lambda. We're going to have energy total is number of photons times energy of a photon. Were you there when we did that part in office hours earlier?
Just a moment ago, yeah.
Yeah, okay, cool. Right, so just the idea that the number of the total energy we have is going to be that. And then we're going to have wattage times time equals energy as well. Right, so the nice part here is since it's just for 1 second, I just do 10 milliwatts, which is going to be 10 times 10 to the minus 3, which looks weird to me. I'm just going to change that to 1.0 times 10 to the minus 2. Because 10 times 10 to the minus 3 looks weird to me. So I'm going to have 1.0 times 10 to the minus 2 joules per second times 1 second is going to give me 1.0 times 10 to the minus 2 joules for my total amount of energy. Then I can go ahead and plug that total energy in. My total energy. And I can have 1.0 times 10 to the minus 2 joules is equal to the number of photons times hc over 1.086 times 10 to the minus 10 to the positive 3 nanometers. I got to do some conversions. 10 to the positive 3 nanometers is 10 to the positive 3 times 10 to the minus 9. That's going to be 10 to the minus 6 meters. Was that conversion okay? That was a pretty quick conversion. 10 to the minus 6 meters. And now I'm just solving for a number of photons. H is a constant, C is a constant. The thinking parts, so the important thinking parts here, there are several important thinking parts, right? Because that was, like, I flew through that and it was like, when I did it, it was like, oh yeah, of course. Like, all of them make sense. But there's some really important thinking steps. First off, recognizing that we needed this energy of a photon equation, not trivial, right? We have to think, we have to be able to look at this and be like, I've got a wavelength, it's talking about energy and photons, I probably need this equation, right? There's no place that tells us that's implied information. This equation of the total energy is the number of photons you have times the energy of each photon, again, not explicitly given anywhere, something that we kind of have to think through of like, well, how do I get a total amount of energy when each photon has such little energy? That is also a critical thinking part. this wattage times seconds, this one, not so bad because it's just multiplying by 1, but that, for me, the reason I'm okay putting that in this class is because there's some amount of unit analysis that's necessary there, where you can look at it and be like, well, I've got to get rid of the inverse second, so if I've got joules a second and I've got seconds, I can just like multiply by 1 second and get rid of that and get energy. Also not trivial, not just like super obvious and easy to do. There's all things that we kind of have to think through and have, like, so this problem is kind of, and you'll notice this happens, like, I start with questions where it's like, calculate the energy of a photon, calculate the energy of 10 photons, calculate the number of photons given this amount of energy, blah, blah, and it's like, they build up and build up and build up, and if we're not, like, a lot of people are doing the homework, I can never tell if people are using the homework, which is different than just doing the homework. You do the homework, you get the point. I made it easy to get the points on the homework. You get your points. But do you go back and look at like the structure of the homework that's trying to build you towards more complicated questions? Because by the time we get to the quizzes, like the graded questions, the quizzes and the exams, it's those more complicated questions that I'm usually going for. Not the beginning questions of the homework that are like the single steps. I'm looking for those questions that are like 2 or 3 steps put together. And this is like a 3-4 step question. Does that make sense? Yeah. Okay.
Might be more of a complicated question, but do you have any advice of what we should do if we're just completely stuck and don't really know where to go? Like
explicit, result, implied. Right? Sure. When you start writing down the
implicit.
So if you don't know the implicit, this is my process for how do you figure out the implicit. You look at what stuff you were given and what you're trying to get to, and you start looking for, okay, what pieces do I have? What equations go with those pieces? And you start just finding, like, if you can find the first thing that's like, oh, I've got concentration and volume, that's going to give me a moles. Okay, now I've got moles, I've got molecular weight, that's going to give me like, you start looking for those pieces, and hopefully you can start finding the implicit, right? And it's tough, like, it's like, if you can't think of the implicit, then you missed something in class, and that's kind of like the whole point of the implicit. I try to make it so there's ways that you can get to the implicit from the problem, but if someone hadn't come to any class and came in and tried to do this problem, they wouldn't be able to do it at all.
Yeah, for sure.
And that's the kind of thing I'm looking for, is like, have you been paying attention? Can you figure out the implicit? Like, that's what I'm testing for. That's what all of your classes are testing for.
Sure.
Okay. Let's go ahead. What time is it? I'm going to go ahead and stop recording. We'll do number 3 again, and we'll go from there.